Okay, so before I start, I think I should thank the organizers twice. First of all, for allowing me to give this presentation today, but also for putting it on the same day as both Marcus and Gregor, who have given rather fantastic introductions to both molecular interferometry and multi-path interference. That's it. Let me move it up. Is that better? No? Is there a volume? Okay, so basically what I'm going to be talking about is trying to combine multipath interference experiments using matter waves instead of light. So as a little bit of motivation, let's take a look at Born's rule itself. So Born realized a very long time ago now that any solution to the Schrodinger equation, which I've written here, satisfies the property that the mod square of its solutions are always integratable. So he interpreted this as a probability density for the waves that satisfy this equation. And in that respect, he gave some sort of physical meaning to the solutions to the Schrodinger equation. But what can we do to deviate from Born's rule? So there are a couple of options. The first one is to modify the dynamics. So I can change my Schrodinger equation. So here all I've done is I've added some nonlinearity. And you have to be a little bit careful about what that nonlinearity is, because depending on exactly on its form, you can do some crazy things like violate causality or no cloning. One interesting thing for using matter waves instead of light waves in these experiments is that, of course, they couple very strongly to gravity. And at the moment, we don't have a complete theory combining quantum mechanics and gravity. So it's interesting to look empirically at these sorts of systems. In addition to that, there's the case of these non-classical paths, curved trajectories of particles as they pass through some sort of slit experiment. Unfortunately, as you'll see at the end of this talk, the sensitivity that we realize in our experiment is a few orders of magnitude away from being able to realize this in our setup. So what is our setup? Well, the idea is very similar to Gregor's experiment earlier, only that instead of using single photons, we want to use molecules. So the idea is to use a three-slit apparatus. I've labeled them A, B, and C, and the wave functions associated with each one of them, which is psi A. So we're going to assume the Sorkin parameter from before, where we compare the interference pattern from the three slits to different combinations of double and single slits, and see if they differ from one another. So this is an artistic impression of our interferometer. So we start off with a glass plate coated with a thin layer of dye molecules. So for these experiments, these are phthalocyanine, which have a mass of about 500 mass units. So we launch them from the surface using a tightly focused blue laser beam. So this has a spot size on the surface of the window of about 1.5 microns. And this ensures that after the molecules have propagated about a meter or so, then the transverse coherence is large enough to cover at least a few slits of our operator. So this is the diffraction mask that we're using, and this is the first point where we differ quite strongly from the experiments of Gregor earlier on. So for molecular interference, the separation between the slits needs to be much, much smaller than it does for optical interferometry. So actually, to see any sort of reasonable fringe pattern further down our interferometer, we need the separation between these slits to be on the order of tens to hundreds of nanometers. So this is quite restrictive when it comes to covering slits. So for our particular experiment, we decided that we would cut individual slits into the mask and just rely on the quality of our fabrication in order to compare the different contributions from triple, double, and single slits. So after the molecules have passed through our diffraction mask, they stick to a glass plate again, where they stay fixed. So this is another difference to photons. So when you detect a photon, you typically destroy it. So our quanta, once we've detected them, they stay there for weeks at a time. And actually, we measure the light that they scatter over about 20 seconds. So in the particular system that we're using at the moment, we have single molecule resolution. So we can count individual molecules in the surface of the screen. And by looking at dilute regions of the screen, we can attribute an average scattering rate. And from the number of CCD clicks we pick out, we can attribute an absolute number of molecules So this is the next difference between a molecule interference experiment and a photon one. Because the separation between the slits is so small, whereas the separation between the fringes is much larger, it's actually impossible to measure the difference between slits B, C, and slits A and B. So we just simplified things. So this changes this Sorkin parameter epsilon slightly. So I've rewritten it in terms of the number of fluorescent photons, or the number of molecules, sorry, on the surface for a triple slit, minus twice the double slit with the separation of D, minus the double slit with a separation of 2D, plus the sum of 3 times the slits. This is almost exactly equivalent to the conventional one. It's just that we don't have the resolution to be able to discriminate 100 nanometer shift on fringes about 100 microns. Okay, so to the diffraction mask. So because we can't cover and open our slits, it's important that this is of extremely high quality. So it's fabricated from a 20 nanometer thick amorphous carbon mask, written using focused iron beam with a precision of less than about 5 nanometers. Now, the opening of each slit, A, is about 80 nanometers, and the separation between them is 100 nanometers. So this is a triple slit here. So this entire mask is about 20 microns high and about 300 microns. So we chose to have such a large aspect ratio for this in order that the flux was as large as possible. Because the aspect ratio is so high, we also have to have some support structures transversely to stop the carbon, rolling up. So you might be worried about surface interactions, and certainly we're going to have surface interactions in this experiment. But they only really become a problem if the edges of the slits are corrugated. So we deliberately chose thalassine because it doesn't have a very large dipole moment. And we deliberately chose carbon because it's electrically conductive to minimize these interactions. In addition, the transverse coherence of the molecules when they arrive at the mask is much, much longer than the correlation rate. So the wave function explores a region much, much larger than any roughness. Of course, in future, it would be interesting to repeat these experiments using light gratings instead of material gratings. And actually, we have a paper on a similar topic, the Leggett-Garg inequalities, where we've put forward these ideas. So what do the interference patterns look like? So here you can see a single slit diffraction pattern, 2 double slits, and a triple slit. The difference between these 2 double slits is that the grating period here is twice as large. So each measurement that you can see here takes about 8 hours, and we have about 10,000 molecules deposited in each particular screen. To give you an idea of the density, it's about one molecule per square micron. So each of these is about 80 microns wide and about 280 microns. So by subtracting these different images, one from the other, in accordance with this formula for epsilon, we can map out some sort of 2-dimensional deviation from effectively from. And you can see here that the deviation is typically about plus or minus 1 molecule across this entire region. So you might be wondering why the interference patterns have this shape, where the separation between these fringes varies as a function of height, and that's simply because we don't have a monochromatic source. Our velocity distribution is relatively broad, and as the particles fall under gravity, so we have fast ones at the top, slow ones at the bottom, the de Broglie wavelength changes and the fringe separation changes according to effectively the Bragg direction. So by measuring the separation between the plus and minus 1 diffraction orders, we can map out the velocity of the particles as a function of the height on the screen. And that's what you can see here along with some theory for what how the velocity should change as the particles fall. And here you can just see where we've mapped out the velocity distribution. And we've also recast it in terms of the de Broglie wavelength, which the full width half maximum varies between about 2.5 picometers and 5 picometers. Okay, so this measurement of the deviation epsilon is fine, except for the fact that it's sensitive to the total number of particles that you're working with, which is obviously not good because the longer you run an experiment, the larger this number you get. So in some way, we need to renormalize this. So this is the kappa parameter that Gregor was talking about earlier on this morning. Now, we actually chose a slightly different normalization method to previous experiments, primarily because in our gratings, the height of the central fringe is somehow dependent on the interaction energy of the particles with the grating. So if you imagine in a light grating, as you vary the intensity, the side fringes increase in height and decrease in height depending on the intensity. So we decided instead of that, we would take the total number of molecules within a given bandwidth of the Broglie wavelengths, primarily because the total number of molecules should be conserved at low energies. In principle, if you know exactly what your interaction energy is, you could relate this in some way to the peak intensity, the center of the zero. So this here is our measurement of kappa, averaged over 5 runs. That's about a week's worth of data. And you can see that it ranges between about 0.08 and minus 0.08. There's an enormous amount of information contained in this image. So we span about 80 microns transversely, and well, the interesting data is sort of up here in the range of about 2.5 to 5 picometers. But in order to try and get a better handle on what's actually happening here, I've plotted a couple of two-dimensional plots as well. So I've just drawn a line straight down the middle of the zeroth fringe, and that's this data that you can see here. The step size varies as you move through different de Broglie wavelengths, primarily because the position on the screen is nonlinear in velocity. So you can see that along the central fringe here, the absolute value of kappa doesn't exceed about 10^2. Similarly, so the 3.5 picometer de Broglie wavelength is just a peak in our velocity distribution. So it's where our statistical error is lowest. You can see the variation is slightly higher, but it's of approximately a similar size. Okay, so in summary, I believe this to be the first direct measurement of kappa using matter waves, certainly using molecules. Phthalocyanine, which has a mass of 540 AMU. We achieve a bound of a part in 10 to the 2 over the entire de Broglie wavelength range of 2.5 to 5 picometers. At the moment, we're limited by the statistics, so it's just the total number of molecules per unit bandwidth that we detect. So if we had a coherent source or monochromatic source, that would make life a bit easier. Likewise, if we had a brighter source, it would improve the statistics and decrease the acquisition. So what next for this kind of experiment? So it would be interesting to move to the near field, where I think the sort of one loop corrections to the intensity pattern should be larger. It would also be interesting to move to particles of higher mass, which have a larger gravitational path. As Marcus mentioned this morning, the mass record for any of our interferometers is about 2,000. Likewise, moving to a near field interferometer would allow us to use more slits, where the flux is higher and the noise should be. In addition, a near field, all of our near field interferometers at the moment have gratings made from light. So any systematics introduced from the Casimir-Polder interaction, or the Van der Waals interaction rather, will be removed. So with that, I'll thank you for your attention, and I'll also thank the interferometry guys in Vienna, so Marcus, myself, Christian Brand and Christian Knobler, and the guys in Israel who fabricated the grating mask, so Wojciechowski and Ivan. Thank you very much. Do I have time for questions?
Thank you very much.